The day we launched Text-to-CAD in December of last year, we had 13,000 CAD files generated the first day of launching the platform. And the infrastructure engineers had quite the day that day because we were expecting inbound. We were not expecting inbound at that level.
Welcome to Sorcery. I'm Molly O'Shea, founder of Sorcery, a weekly top VC deals newsletter highlighting the top GPs, founders, and deal announcements leading the next innovation cycle. Today, we have Jordan Noone, executive chairman at Zoo and founding GP of Embedded Ventures. For context, Zoo is a research and infrastructure company building the tools to introduce AI to all aspects of hardware development. And previously, Jordan co-founded Relativity Space at age 22. Which was most recently valued at $4.2 billion. This is a fun technical conversation, and I hope you enjoy. Hi, Jordan. Thanks for joining us.
Happy to be here.
Well, to start, I'd love to learn more a bit about what you're building with Zoo.
Zoo is a company that's building not only the world's first computational geometry engine based in the cloud, it's GPU optimized, API accessible, cloud-based, and but also able to build tools that bring AI to hardware development that have never existed before.
Okay, so that's a lot. Maybe let's take a step back and really contextualize this, right? So how big is this problem and who exactly are you servicing with this product?
Hardware development touches almost every company today. And whether it's obvious or not, everything in the world goes through hardware, whether that's network equipment, autonomous cars, and furniture within those companies. Every single company has hardware development somewhere underneath what they do. And so for us, we view it as about $1 trillion sized market. That's both the labor and the software license costs for actually running those hardware development programs. And so our view was that we had to bring that industry to the 21st century. And it last was updated in the 80s. And it's still an industry fully driven by engineers with a mouse clicking on a screen. And we wanted to see what we see in every other industry today of automation and machine learning enter that industry in a way that brought the entire industry into kind of the modern era.
Since you're disrupting 60 years of software in $1 trillion industry, if you could break down a little bit further what that current workflow looks like for the hardware development cycle, maybe more specifically against maybe the aerospace industry, given your involvement, what are the steps in that process? How long does it take? How many people are involved?
Yeah, so most people get surprised that the state of the art in hardware design tools today is an engineer with a mouse clicking on a screen. And people have generally had some visualization, some opportunity to see someone using a CAD tool called computer-aided design, and where that's someone drawing lines and sketches on a screen. And that was the state of the art. Essentially rolled out the first product to do that effectively on a digital computer was Autodesk with their AutoCAD product. And people think that's how it was 40 years ago. It must have improved since. And sadly, it has not. It's been an industry that has generally been forgotten by modern software development. It's definitely been forgotten by the modern machine learning kind of automation push. And so the day-to-day presently, for all companies designing hardware, again, ranging from, a pencil all the way to a rocket or an autonomous car or a server rack, and is literally a fleet of engineers clicking on that screen, drawing every single line, circle, corner, every surface that goes into those is manually defined by a human with a mouse and clicking on a screen. It's very laborious, and it results in team bloat, where if you have a part and the engineer next to you has a part and those interface to each other, now you need to cross-communicate, generally manually again. How does this part interface with that part? How does part 1 interface with part 2, interface with part 3? It's a very, again, labor-driven, very slow process that ends up compounding, the number of times or number of parts you have interfacing squared. That's the number of interfaces you have. That's the number of engineers you have having kind of cross conversation on how to make all these parts fit together and work. So again, very labor driven, very complex, very archaic by modern computation standards. And so our view was, how do you shift that entire industry into one that is driven by what we see again in every other industry? Automation, machine learning, and code. And it comes down to what we viewed as a data challenge. The way that the current hardware design industry is built is that in order to interface with a hardware design, you have to interface with the mouse. And the only way to interface with those, you can't use code to access those designs. You can't use code to access those geometries and use those to interface with something downstream. And you have to do it with the mouse. So our view was, if you built what are the engines, what we call like a computational geometry engine, that's what talks to the geometry, generates new geometry, and how that intersects with previous geometry. And you had to build that entire geometry engine from scratch and build that in a way that was not only high performance, but also had the accessibility that you could interface with that in a dynamic way and scale that with cloud computation, so that you weren't limited by either the ability to access your geometry engine or the ability to scale the high performance compute side of it into a level that you could not only automate tools, implement tools, but train machine learning models on top of that.
Within that, you mentioned a couple of industries, and so there are large legacy industries that haven't caught many of the waves of innovation throughout time because, they're more laborious. It's like physical demand. What exactly are you targeting with Zoo? Like, is there a particular part in the process for their hardware development? Is this like a specific niche in the industry?
Yeah, to narrow it down, we start at the design phase of the hardware development lifecycle. There's various elements that go into generating design and getting something into production for an actual, engineered, manufactured part. And we start on the design side, where it's actually generating the geometry, generating what eventually gets made downstream. We don't touch that downstream area yet. We will be soon. And the intent of that is to capture essentially industry-wide. Once you have the geometric primitives, all those shapes, all the computation to combine those shapes together into more and more complex geometric parts, engineered designs, then there's no one specific industry that's optimized for it. It's for all of them, because those primitives can be combined in a way that forms shapes for any industry. But the people who we tend to see the most adoption from are people that see software development and hardware development side by side. There's an asymmetry there, where in modern software development, you can write code at scale. You can push that to the cloud to dynamically allocate that, to dynamically scale that. Then you can write unit tests. You can write what is called continuous integration workflows, where you automatically make a software edit that automatically gets tested to verify that works well, and that automatically gets propagated to the entire world, whether that's local data centers, updates, websites. It's not something where you're having manual reviews of those changes. Then the majority of that tends to be automated in a modern software development ecosystem. So we see many customers today, our customers we want, and as well, where they have the benefits of modern software development, the cloud, automation, scaling there, and then they have hardware development side by side. So take, for an example, a robotics company, an autonomous car company, an aerospace company. They tend to have both those areas of extreme software development and extreme hardware development. But their software engineers get automatic workflows, automatic pipelines. Your hardware developers, they need to make a change. They're booting up a 1980s license manager. They're loading their software. They're loading their files for hours. They're making a change manually. They're updating a drawing so they can communicate with their machinist, their manufacturing engineer. And then they're calling up that machinist saying, hey, can you make this part? Can you make this change? And it's a very manually driven workflow. And that asymmetry we take leverage of. And because it's these companies that see the benefits of software, they have the ability and the talent base internally to adopt modern software, and they're bottlenecked because of their hardware development changes. And that crosses, again, like almost all the innovation, the most valuable companies in the world today live at that intersection of hardware and software. So it's a very high performance customer cohort. And they're the world's leading companies, world's leading startups that have that specific challenge.
We talked about this a little bit when I came to visit, but in terms of your core products, could you break those down, starting with your core product right now, and then are you going to be building this to an end-to-end kind of stack, or is it going to be focused on one particular area? And feel free to go in as technical as you want. But would love to kind of break down your core products and how you're going to be expanding.
Yeah, I'll start with the history of the company and where we started in the product stack. But our view was foundationally, it's a data and data accessibility challenge that bottlenecks the industry. If you can't talk to the data effectively, you can't. And when I say talk, I mean talk to it with code. then if you can't talk to it with code, you can't build tools, you can't build machine learning. You can't build a machine learning model if you can't talk to the underlying data. That's kind of the fundamental bottleneck there. So our view was we would start with this geometry engine. That's the world's first GPU-optimized, cloud-based, API-accessible CAD engine. We built that from scratch. So that's CUDA, which is kind of GPU-level machine language, CUDA-level implementation of those computational geometry algorithms. It's a lost art. Many are not trained in it anymore. The skill set that developed the first CAD engines, those were back in the 80s. Those are still used today underneath every other tool. It's a lost art of a skill set. That engineering generation that was very mathematics, kind of fundamental algorithm focus is now in the ML world. They got lost from the computational geometry world. So we built that team. We built that CAD engine for the first 2 years. And that CAD engine deals with all of the intersections, the generation, all of the geometric manipulations that allow those parts to come from nothing and turn into a shape on your screen. And we built that engine, and then we started building tools on top of that engine. Those tools are the more user-facing products. The geometry engine is behind the scenes powering everything the company does. And there's 2 products we've shipped to date on the tool side. One of those is a tool called our modeling app. That is a CAD interface, CAD being computer-aided design, a CAD interface where you can edit a part with your mouse, just like any engineer would do in any other CAD software today. We shipped that as an implementation to demonstrate we could build tools on top of our API and as an entrance point that one-to-one matched what engineers use today in their current design toolkit. But we started adding in capability to that, where the first thing we wanted to do was make it so that you could interface with your parts, not only with the mouse, but with code. And that code allows scripting, automation, scaling, things like equations and database lookups and logic, things that sound obvious to anyone who's done software before. Of course, you'd think that software could write a loop that changes the geometry of a feature, or that you could have some logic in there to say if a certain feature was over a certain size, model it this way versus another way. Those seem like basic concepts to a software developer. Those have not been accessible to a hardware developer for the entire history of the hardware development world. Those were just never accessible tools. You were making those decisions yourself and making those changes with a mouse. And so we built in that ability, starting with the modeling app launch last year, that you could add in those changes via code. That's built into the modeling app. You can, again, edit those parts as you would traditionally. If you want to edit with code, you can edit with code. And then we shipped that last year to strong fanfare of people who wanted to see that implementation. And then we took it a step further. The second tool we launched is a product we call Text-to-CAD. That is like a ChatGPT interface, but you end up getting a CAD file back. So essentially generative AI for the hardware design world, and where you can interface again with a chatbot. And rather than, again, going to the mouse, clicking on a screen, making those changes manually, you can request those changes. You can make a part from scratch with Text-to-CAD. And that, again, brings the generative AI world into the hardware design world, an area that has not been touched historically. Then that's only possible because with our geometry engine, we can talk to the data. And if you can't talk to the data, you can't build an ML model. I always bring it back to that.
Hey, we'll get right back to the conversation after a word from our sponsor. Sorcery is brought to you by Archer. I'm genuinely amazed at what Archer has been able to accomplish. Archer's goal is to transform urban travel, replacing 60 to 90-minute car commutes with estimated 10 to 20-minute electric air taxi flights. They are safe, sustainable, low noise, and cost competitive with ground transportation. Archer's Midnight is a piloted 4-passenger aircraft designed to perform rapid back-to-back flights with minimal charge time between flights. Learn more about how Archer is set to open up a new world of opportunity for passengers by providing safe and efficient access to people, places, and events across the communities they live. Visit archer.com.
Right now, we're doing a push for what we call version 1.0 of both of those products. Those will actually merge together, that rather than generating text-to-CAD and having a part, you can now do that in the modeling app and then make downstream changes. The benefit of that being, and the more relatable case for many people, is doing like a AI image generation or AI video generation. You get 95% of the way there, and there's one feature in your image that you need different, and there's nothing you can do about it. Then, other than try to slightly change your prompt, slightly perfect your prompt. It's a huge bottleneck in the generative AI industry. You can change text, You can change certain things that generative AI can do. You can't change some of these more complex abstractions like imagery, video, audio. And so what we did with Text-to-CAD is we actually now built that in to our modeling app, and where you can generate with a chat prompt, you can edit with a chat prompt, and you can edit manually. And that gives the end user 3 different ways that they can edit their designs. They can edit manually, as they're used to historically with the mouse, clicking certain geometric features, clicking certain surfaces, defining those manually. They can edit via code, that code defining what the part does, or they can edit with a chat prompt. And that gives the user, regardless of their background, regardless of the complexity of what they're doing, the ability to make that decision on what is best for them on generating these hardware designs. And again, gets the industry past what was just 2 years ago, where you only could interface with a mouse. Now you can do mouse, you can do it with a code prompt, and you can do it with a chat prompt as well.
Interesting. So I have like 2 kind of competing questions here, but I'll lead with one first. So given the nature of the industry and engineers not really having access to other types of tools out there, this is a newer tool. What is the onboarding process like to get people trained into using, your Text-to-CAD offering or your other offerings? Is it, self-serve? Do you have to have someone help onboard them? The competing part of this, right, is that I do know that you open source some of your code. So what is the process there? How do they interact?
Yeah, our view was that it's a very kind of young and nascent sector when it comes to building and developing these tools. And to expand on the product suite that we offer, we have our user-facing tools like Text-to-CAD, like the modeling app. Again, those are getting merged together, in the coming weeks here. And those are meant for a mechanical engineer with zero code knowledge, zero code experience. That was me 10 years ago. I'm a mechanical engineer by training. I never took any coding classes in college and self-trained entirely. So I'm kind of code curious, but again, kind of that mechie at the core. And that's what we've baselined for our tools, what we call the tools. Again, external facing is that you don't have to have any software development experience. We also offer the geometry engine and ML capabilities via our APIs. And the intent of that is to be extensible. If you want to build a tool automating a design workflow, if you want to build a tool that has manufacturing awareness into it, where you're, let's say, auto-generating manufacturing instructions for your CNC machine or for your technicians, that does start with the geometry. You're talking to the geometry, you're understanding what the features need to be made, you're understanding surface finishes, you're understanding tolerances. Then there's bespoke use cases there we can't design for, but there are customers who want to extend that capability. So we have those APIs exposed. And the way that I reference that is if you look at like OpenAI and what they do. They have ChatGPT, their surface level product. You don't need to be an ML developer to use ChatGPT. You just put in a text prompt. That's where our tools live. And then OpenAI has their APIs, which are extensible. You can build tools on them. There's hundreds of companies, thousands of companies that have built products on top of OpenAI today. That's where our API lives. Then is those customers who want to extend workflows. Some of those are single individual contractors that have some need. Some of them are hundreds of thousands of people companies. Some of the world's largest organizations, they have those same exact bottlenecks. And we've seen usage again from day one companies 100 years old with hundreds of thousands of employees, and who use the APIs for that implementation. And so as far as entrance point and onboarding, to your original question, Molly, those tools are meant to be self-served. Then you can start using them. They're very intuitive. There's training available. Then that again is rooted in me as a day one, mechanical engineering graduate. What is the tool I would have wanted to use that I was ready to use? Should be a similar experience with some nuanced changes that we provide, documentation and training for. But it should be native to what you expect from a CAD tool. And the reason we started open sourcing those tools is one, that those tools still drive traffic through our API. That's where we monetize the majority of our incoming traffic. And is that they still create traffic on top of us. And we don't necessarily defend what is the open source tool. We defend what is behind the API as far as what is our proprietary stack that we develop as a company and where the defensibility lives. And that gives what I had mentioned of that very nascent, very early ecosystem of tool developers in our ecosystem a starting point where they're not starting writing their program, their company's proprietary software, their workflow, looking up API documentation for us. Then they can go to a working tool. They can go to an add-on we've built. Then they can go to one of these products that shows how to build a tool around our API calls. And that's been twofold beneficial for us. One, it helps accelerate what is that tooling development by third parties on top of us, on top of the APIs. Then because it gives them a starting point. But it also does what we call dog fooding our own software, where our view was, and we went through this last year, that if we expect other people to be building tools on our APIs, how do we expect them to do that if we can't even do that? So we decided to start doing some experiments internally of building these tools, the first of which was the modeling app that came out in October of last year. Then it took a couple months last year to build the majority of that. And that was our working experiment of turning what was API capability into functional products. It was an amazing working experiment because we realized in launching that how many people actually wanted not only the APIs for extensibility, but the customer cohort that wanted just an out-of-the-box product that's generally the more mechanical engineering-based, less software native customer cohort. They wanted a tool out of the box, high performance that they could use. And then we've added extra capability in there over time. So we do service both. The development side is very bespoke. When we're facing developers, we work with them generally hand in hand, especially these early adopters where they're building companies, they're building solutions on top of us. The day-to-day cohort that uses the tools, the mechanical engineering facing tools, it's generally very intuitive on onboarding. But we still provide them as much support as we can.
Before we go too far, because I'm sure it can continue to go down the technical route, I would love to just dial it back and talk about the team. So maybe starting with you, let's learn more about you and your background, and then would love to learn more about Jessie, your CEO, and her background.
Yeah, I'll start with me. I'm an aerospace engineer formally by training. Went to USC, studied aerospace engineering there. Ran USC's rocket propulsion lab, became the first student group to fly a rocket to space. I was the first person in the world, youngest person in the world to get FAA clearance to fly a rocket to space. So very early start to my career. We first flew one of those space shots. I was 19. Overseeing that group. It was 0 to Mach 7 in 13 seconds. So by far some of the highest performing hypersonic rockets in the world. We were doing those as teenagers in the back of a college lab for $50,000 a year. And so we did some great work there. That was a huge accelerant to my career. And we did all the design, the regulatory work, all the propellant manufacturing, all the machining, all the simulation, all the FAA submissions. We did that all as a student group there. So pretty one-of-a-kind student experience that we went through there. That got me a job straight out of college at SpaceX. And at SpaceX, I was a valve designer, propulsion designer on the Cargo Dragon and Crew Dragon spacecraft. That was subsequent to a couple years interning first at HRL, which is the old Hughes Research Lab in Malibu, and then Blue Origin, which is Jeff Bezos' space company up in Seattle. Between all those experiences, I loved the space industry, but even SpaceX was starting to feel at a size that it didn't feel like as much of a startup anymore. And so I wanted to go out back on my own, running USC's lab, having that full independence of a small group, setting the direction of that group, and having kind of the accountability to do everything there. And gave me the feeling of feeling still even a little, as an entry-level engineer at SpaceX, a little kind of trapped. And so end of 2015, myself and one of my USC lab leads that had been one of the people with me at USC, and we started Relativity Space, then to 3D print rockets and build the world's largest metal 3D printers. I'd seen exposure to 3D printing through my work on the SpaceX Dragon capsule. Wanted to see that scale, wanted to see that taken to the extreme. So us as two engineers, never took a business class, a finance class, a legal class before then. We started pinging investors. We got into Y Combinator. We got an entry check from Mark Cuban, and we hit the ground running end of 2015. Relativity is now a 1,200 person company, raised about $1.2 billion in private capital. It's headquartered down in Long Beach here in Los Angeles. And I was chief technology officer for the first 5 years of the company, managed the rocket side of the company, the printer side of the company, government affairs side of the company. for a number of years before stepping out in 2020. That probably segues well into my time with Jess, then with what was originally called CAD and what's now called Zoo. We did that rebrand end of last year. And but with Zoo and Jess specifically, Jess comes from a probably equivalent in shared software, hardware development experience that I do, but in the opposite direction. She was an early program manager at Docker. She has an amazing following and set of experience within the software infrastructure community. That's that same community that is known to automate the development, automate the deployment of major software implementations and cloud implementations today. She started in that world and then started a company 5-6 years ago called Oxide Computer Company. And she was chief product officer there. What Oxide does is build from bare metal up server racks for companies that are not the Amazons of the world, where they're making their own data centers, their own data center hardware, but they're bigger than the companies that are, let's say, bolting together a bunch of Dell equipment. They're in this middle where they need highly configurable, cloud scale deployment style data centers that are local. And there's no hardware solution for that kind of middle tier of companies where you're not making your own racks, your own equipment, but you need higher performance than bolting together some off-the-shelf components. So Oxide built those up. Jess was, again, their chief product officer. And the way we had met was Jenna, who's our third co-founder. She had reached out to me on Jess's behalf. Jenna was an investor in Oxide in her previous life. And Jess's question to me was related to hardware design automation. She had noted how much automation and digitization we had on the factory floor with Relativity. And her question to me was, there were things they were doing internally at Oxide. Things like they would move a bracket that was holding one of their server racks together. And 3 weeks later, they would finish running an analysis that showed that they now broke their thermal flow path out of the server rack. And they'd have 3 weeks of wasted work. Or they'd try to even just export a file for one of their vendors. And it would be 3-4 hours of computation on a single machine just to export the file, into a format where they lost a bunch of intermediary data so that they could send that to their vendor. And her question to me was, we did all this digitization and automation at Relativity. What did we do to automate and digitize the design side? And I had a very lackluster answer for her. We use the same bad tools everyone else in the industry does. And which was very frustrating to her because she came from a perspective on the software side that if you need automation, you need development, you build these tools, you automate these tools. If your tool is a constraint, work on the tool. And that level of mantra just kind of never came into the hardware design industry because it generally has been so far away from the software development world. Software engineers can generally solve their own tooling problems. Then hardware engineers, they can make a factory floor tool. They can't make a software tool to solve their own challenges. So that conversation kept essentially bootstrapping for years then between us, where we wanted to see a company that had done, implementation in this space. We weren't satisfied with what we were seeing in the industry. There's a lot of companies that make, porting of engineering software to the browser, but there's no change in the day-to-day workflow. Then you see companies that we call like dashboard companies. They make cool GUIs, they make cool integrations. Doesn't change the end or the day-to-day workflow for those users. Then there are these small incremental changes and no one's made a dent. There hasn't been an engineering software IPO since 1986. It's been 40 years of the same major incumbents. No one has made a dent in what that design workflow looks like. So we were looking for what we thought could be a good company, a good investment in the space. From our work at Embedded Ventures, we wanted to flush out that digital engineering portfolio for the fund, and eventually settled that we had to do it ourselves. We were very dissatisfied with what was out there. So we hit the ground running with what, again, was CAD back in 2021, spun that out of the fund. Jess was chief scientist for a while she was transitioning out of Oxide. I was CEO for the first 2 years of the company. And then as the company got to a real size, and then Jess Jess came on full time then to CAD. We promoted her to CEO, myself to exec chairman. She runs the day-to-day internally. I run the day-to-day externally for the company. That's kind of how her and my story kind of interblend together. And it was out of, lack of solutions at our previous companies. I think we're very lucky to have both have that shared opportunity of working on extreme hardware and extreme software development in a way that is not only mirrored, but, kind of opposite of each other in sequencing, which has led to the kind of tools we've developed as Zoo, because no one else in the industry has been anywhere close. You see hardware engineers developing very surface level solutions. You see software developers generating solutions that don't actually solve hardware engineering problems. And we hit that blend perfectly of tools that are extremely complex to develop, a very high barrier to entry from a software perspective, but do solve the day-to-day challenges of that mechanical engineering end user.
Wow. And it seems like it's like a very seamless evolution of two different kinds of sides of technical expertise and engineering, and you were able to do that pretty compatibly. What is the makeup of the rest of the team? How big is the rest of the team? Are they all US based, or is this kind of spread out?
Yeah, so Zoo's about 20 people now. We'll be about 50 people this time next year. And so we're starting to enter a pretty big growth spurt. And that team split up between a number of pretty deep technical areas. And the first area to highlight and where we started was on the computational geometry side. Again, that's a pretty lost art within, basically all engineering areas, across the world today. There's not a lot of computational geometry engineers left. And but we have a team there and built that team from scratch. That's the team that develops the actual computational geometry engine that's underneath every single part of the company. And I don't think there's any other company in the world that's built a computational geometry engine in at least a couple of decades. Most people still are extremely caught off guard when we say that we built our own. They say it's impossible. They say the skill set doesn't exist anymore. And we show them what we have, and we show the results. So that's where we start as a company. We have a full team there on the computational geometry side. We have an ML team. That ML team is responsible for, once you have that computational geometry engine and you can talk to the data, how do you turn that into things like Text-to-CAD, where you can correlate in an ML model the functionality of a part and the sequence of geometric features that create that part. And so there's an ML cohort within the company now that handles that part of the stack. We have a set of infrastructure engineers as well. We have a non-trivial infrastructure stack as a company between scaling the computational geometry engine, scaling the ML models and the training there, and then scaling the APIs and the dynamic nature of allocating that not only to our own tools like Text-to-CAD and the modeling app, but third-party tools that are also built on top of the API. We have to support all of that simultaneously. And then we have a set of more front-end engineers that do the tools like the front end for Text-to-CAD, the front end for the modeling app. Those both have, especially the modeling app, some non-trivial complexity built into the code, manual change integration. Then where there's a dynamic linking between what you're doing manually and the code generation that's on the back end for generating those. And then we have a set of people, I include myself in this, that have that mechanical engineering background. Then that's been very helpful for testing the products, usability for the products, onboarding and integration with current users, current workflows. And but also they've been very valuable on generating what we call virtual data sets. And for the Text-to-CAD training, we have a variety of data sources that we use for those models. But one of them is virtual data sets that we generate internally. We can do that. Again, we can uniquely do that. Because we have the geometry engine, we can dynamically scale that. We can create millions of geometries off of first order, second order design rules that we parallelize the creation of in the cloud. We analyze the performance of those and the geometric features that represent those with the geometry engine and can pipe those into the Text-to-CAD workflows. We use that to fill gaps where we either don't have good data there. We have customers that highlight that there's a gap in the Text-to-CAD model training. The day we launched Text-to-CAD in December of last year, we had 13,000 CAD files generated the first day of launching the platform. And the infrastructure engineers had quite the day that day because we were expecting inbound. We were not expecting inbound at that level. And even some of the customers caught wind of it before we had even done the announcement. And they were starting to tweet up a storm on a capability that I don't think anyone was expecting to exist in 2023. So we have the team split. It's a very unique team composition. And I don't think any other company has that level of, ML, computational geometry, mechanical engineering, infrastructure deployment, and wide. And then through this next year, as we grow the team, as I mentioned, it's going to be doubling down on The ML side of the company, the computational geometry side, those are obviously the backbone for the core of the differentiation that we have. And then a huge amount of scaling still on the infrastructure side. We're starting to build out our first local data center. Then for our own GPUs, both for the geometric rendering side and the ML training side. We use those on both sides of the stack there. In addition to a couple new initiatives that we are kicking off through this next year as well.
Awesome. Okay, so highlighted that you will be hiring, so that's
We are
exciting. And I guess this actually takes a good transition and will map out, I wanted to talk about your office a bit. So given the kind of background of the roles that you have on the team, this helps map out kind of like the blueprint. Like, thank you again for showing me around the office and what will become the office. But you have like a couple different areas, right? So you have your GPU room, you have the quiet area, you have like more like desks and call booths and like all that kind of thing, and then you have like the machine area. So given that, I think it would be really cool to kind of walk through why you're kind of constructing it this way, but also why it's important for you to go down to the metal and actually test things for your customers in-house.
Yeah, no, I can expand on all of that. We'll start solely on the local data center side, just to highlight that. We are as a lot of ML companies are, but very GPU intensive, data intensive company. Then, unfortunately, between Jess's background, the rest of the company's background, we're in a very easy spot to build out our own local data center equipment. And that's the background of, a quarter of the team. And so we're doing that for a combination of cost savings reasons. And then as we get ready to scale even more as a company in the subsequent years, we want to build the foundation of that team internally because that'll become a bigger and bigger effort for the company as our own local data center equipment and support, given the scope of what we're doing on an ML side. You see these massive numbers for training costs for, some of the LLMs out there and big training models. And we do foresee ourselves becoming a company that's of that scale where we're not training LLMs for, text's sake. We're doing it for geometric design's sake. And if you're going to keep going down that path, it's a very infrastructure heavy company. So again, we want to plant the seeds for what that looks like internally with what is our first, I'd call it like a prototype data center. Building up the team, building up the cost model, building up the vendor relationships to get there. And then we have the other side of what is the current factory. And that you were talking about, and we've hinted at this a bit publicly, but we haven't spoken about it yet, where it's like, why do we need a factory? Then we're a software company, we're a SaaS company. Why do you need something out in the factory? And the way that we viewed it and the way that we're messaging it now is that we've never been just a design company. Then that was just a natural first step to build on top of the geometry engine. Then we view ourselves as a full hardware development lifecycle company. And what goes into that? That's design, that's manufacturing, that's engineering analysis, that's supply chain, that's financial modeling, and that's, insurance services on top of that. There's a whole suite of things that it takes to get from what is just a concept or an idea of a product into something shipped out in the world. And that whole, what again, I'd call like life cycle development. And we're in that transition and growth phase now, where we've started to really get a foothold on the design side. And the example I like to give to extend the workflow question you had earlier, now let's say we've had version 1.0 of the modeling app and Text-to-CAD out. We have people auto-generating designs. They can edit those in their design app. Then what's next? You need to go get your part made. What are you going to do? Are you going to go start flipping through the yellow pages looking for a machine shop? Are you going to email, request for quote at machineshop.com? Then it once again becomes this very manual, very labor-driven process. And we find ourselves in this very unique spot because we are responsible for the geometry engine and what are those data rails behind the entire industry, that we can start moving downstream. And that's a huge advantage for our customers because, again, on workflow, you have your AI-generated design or your manually generated design, whether it's in our software or not. And now you need to go get it made. What do you start doing? You export the part, you make a drawing, you call up the person you found in the yellow books. Then that's not going to fly. That's not an ML first world there. That's not an automation first world. So we're going into the manufacturing software side, starting with CNC tool pathing. That's generating the actual, synchronized motion that happens within, a machine shop. And then whether that's a mill, a lathe, something more complex than that as well, depending on, your kind of factory and your manufacturing process. But generating a CNC toolpath is the expensive part of running a machine shop, especially something doing cutting edge hardware where you're prototyping, you're making one-off runs. Most of that cost is going into engineering labor to generate the instructions for that machine. That happens to be, and very conveniently for us, synergetic with the geometry engine, where that's talking to geometry, understanding tolerances of that geometry, understanding interferences in that CNC machine, where it's geometry of the CNC machine hitting geometry of the part. There's a lot of manipulation to get a toolpath to fit correctly within one of these CNC machines based on a variety of factors, all of which, again, are geometric. And so we'll be adding in that capability not only on our APIs, but within our design tools, where you can have your AI generate a part for you. And you can then generate a toolpath for a specific CNC machine outside of your design world. And all of that would be done in one specific software package. So you're not buying two licenses, two software packages, exporting in between, importing to another, losing a bunch of intermediary data. Then it's very expensive. It's very expensive, very laborious to do so today. That will be one feature addition within our design studio, where we already have an influx of users because of the Text-to-CAD capability. And then on the ML side of the world, for us, we're adding in the ability for Text-to-CAD that you not only can generate a part, I want a gear with this many teeth, I want a case for this iPhone. But you add in the capability that you can say, I want a gear with this many teeth made in this kind of CNC machine. And that's important because you have what's called, design for manufacturability, DFM. It's a cool acronym for it. And that you have this design for manufacturability world where, you finish your design as an engineer and you call up your machinist, you call up your manufacturing engineer, you call up your vendor, and you say, hey, can this be made in this machine? Can this be made with this kind of tooling? Then, can this be made, fast enough? And you're going to get a bunch of feedback there, and you're going to iterate on that design. And you're going to send it back to the machinist. You're going to send it back to the manufacturing engineer. Again, very labor-driven, very monotonous, then very slow, very expensive. And that right now is like representative not only of the manufacturing side, but kind of these deeper problems within the industry where everything has these human touch points in between. There is no way to programmatically do a DFM check, for a part. There's some software that kind of does it. You're still going to be sending it to your machinist. You're going to send it to the manufacturing engineer. You're going to send it to someone familiar with your kind of CNC machine that's making your part. And that's our view, is that can be baked into the ML models. There's no reason you can't extend Text-to-CAD to also do things like design for manufacturing, that it can't do things like tool pathing, that it can't do things like engineering analysis to verify that your part can handle a certain stress load or pressure load. That's where we see the product going step by step, as we start with design, because that's where there's the most defensibility. That's the start of the design process. And then there's a natural domino effect into these downstream areas like manufacturing, because it is all a geometric data question underneath. And if we have those geometric design rails, we can provide our customers with solutions that are much more efficient, much more faster, much cheaper for them because of that. And I guess none of that answers the question of why do we have the factory? And us as a company, we view ourselves as shipping, what is a very robust product for customers with very robust requirements. Then if you're generating tool paths for CNC machines, you want to make sure those are good. You want to make sure that those are making the parts that you say that they're going to make. Then, and our view was, to start for our effort on manufacturing, we want to do that end-to-end testing, where every time one of our engineers pushes a software update on that stack, whether it's on the design side, the manufacturing side, the toolpath generation side, that we push that to one of our CNC machines where we verify the part that's coming out of that end-to-end workflow. If it's text straight to the CNC machine, then that will be a capability that'll come out in the next, year and a half from us as a company, is you can have your text prompt send something to a CNC machine because you have that toolpath generated and processed. We want to make sure what's coming out the other end is correct. And the only way we as a company trust that that'll happen is if we have our own CNC machines and we're verifying that those updates are making the changes that we say they will, or not making, unintended changes within what's coming out. And that also preps us as a company, similar to what I was saying on the data center side of starting to bootstrap that team internally for what is larger expansion. We do have bigger ambitions on a manufacturing side that will come after the tool pathing. But that's, kind of for a later time to share. But we want to start building up that team and capability internally of the CNC machine operations, pushing tool paths automatically to CNC machines, and having that capability built into the design toolkit. All of that will become a much more kind of snowball effort and growing at the company as we get through what is the initial toolpath generation over these next couple months.
So super high touch, high attention to detail, very thorough. You're providing a lot of value to your customers. I appreciate that. And might I add, you are based in Inglewood, which I hear is the city that delivers.
We've been, we moved into Inglewood about a month ago, and this is where that first factory is getting built out. This will be, essentially the office I'm in here right now. Then where we do the toolpath generation, that'll be where the team is. That's where we complete the end-to-end testing for verifying that those toolpaths are sound and that workflow is rock solid, along with the original data center here. This is actually the original Relativity headquarters. Relativity moved into this building in 2016, moved out a couple of years ago, and we moved in specifically for that effort. But yeah, we're not in El Segundo. We're north of that. But a lot of value has been built in this building historically, and happy to be back and doing it again.
That's great. Great historical context as well, kind of full circle. So in terms of funding to date, how much has Zoo raised and by who? What is the composition of the rounds and kind of where are you at in terms of that process?
Yeah, so historically we've raised only about $6 million in private venture capital. Then we've been a very lean, very efficient team. And the first check into the company for the pre-seed round came from Embedded Ventures, which is a fund that myself and Jenna run that we incubated, what was Kitty-Cat at the time, out of. We brought in a set of outside investors with the seed round that was at the end of 2022, about 18 months ago. And that's led to the current growth, current products that we've shipped. That round was led by a fund not too well known in the US. They're UK based, a fund called Venrex. They're a very quiet, very intentional fund. But we've had a great relationship with them. There's a couple of reasons we wanted to work with them based on strategic relationships in their portfolio and their ownership that have paid off very well for us. But again, they keep a very low, very quiet profile. Their website's just a landing page. It's kind of infuriating for everyone who wants to know more about them. But they've been an amazing partner, absolutely amazing partner for us, alongside a set of outside investors, outside angels. Two of the angels in us are two of Jess's previous coworkers, which is Tom Preston Werner, the original GitHub founder, CEO, and then Nat Friedman, who took over the CEO for Tom after that. So two subsequent GitHub CEOs in a row. That's been very flattering for us and helpful on kind of an infrastructure and kind of DevOps level of confidence for us as a hardware first, but very infrastructure heavy behind the scenes company. And and that's been the backing to date.
All right. So as we close out, I'd like to always end on a positive note. So what are your growth plans for the next 6 and 12 months? You mentioned this a little bit throughout the episode, but would love to learn more about that.
Yeah, probably the most exciting feature we're shipping that's customer facing is the ability to edit the text-to-CAD generations in our modeling app. That's been by far the number one feature request for us as a company. We expected that to be the number one feature request. Then it's just taken some time to get to. But that breaks us out from what is the rest of the generative AI world, where you end up with, a generation that's 95% of the way there and you can't change the output. And this is fully baking that into our design suite. And we're expecting a huge inflection point in further usage, further feedback on text-to-CAD because of that. Huge customer cohorts waiting for that feature to ship. And that excites me the most as an end user because that solves my what has been my hardest workflow challenges being a mechanical engineer for 15 years now. And is, you can get the part 99% of the way there with text-to-CAD, finish that final 1%, manually. It's a huge labor savings, huge reduction there. And very much excited for the manufacturing kickoff. We don't expect to have any public-facing manufacturing API or feature implementation for, probably won't be public until end of year. And then it'll mature through next year as we tend to do these early beta launches, get feedback, and then ship the production versions, 6-7 months later. And but that manufacturing kickoff is really for us what takes it from a step change where we're solving labor challenges and bottlenecks within one vertical of the hardware development lifecycle to then doing that simultaneously amongst multiple sectors at the same time or multiple verticals. And where you're automation for design and your automation for manufacturing are now built into one tool simultaneously with limited interaction between you and other engineering specialists that can be consolidated within one person. And that just, again, very excited me as an end user that's been bottlenecked by that for, a decade and a half.
Excellent. Sounds like there's a lot to look forward to, and that you got a lot of work on your hands.
It's a lot to do, but we're happy to build it.
Well, Jordan, it was a pleasure to have you on. So thank you so much for taking the time and for the tour and all of it. Really appreciated to learn more about Zoo and the team and everything that you've been building.
Thank you for having me.
There's no shortage of podcasts and deep dives into the secrets of VC. But the truth is that the world's best venture firms and GPs at their helm still remain an enigma. VC is as much of an art as it is a science. Other shows focus on the now of venture, or even the last 10 years. But what separates the most enduring and generation-defining firms is the subject of a podcast called Turpentine VC from the Turpentine Podcast Network. On this season of the show, you'll hear from Ben Horowitz, Alfred Lin, Mahmoud Hamid, and more. Subscribe to Turpentine VC for the rare and revealing conversations that can only be had investor to investor.